Hello. In today's video, we'll be going into a little bit more detail about reading chemical formulas and how we can use the chemical formula to determine the structure of a molecule. As a review from our last lesson, we know that the molecular or the chemical formula is a way of representing a chemical compound. We know that the molecular formula tells us three things about the compound. First, it tells us the elements that are present. Then it tells us the number of atoms of each one of those elements that's present. And finally, it tells us the number of molecules of that compound that are present. Reading a molecular formula as a review involves knowing three different parts of the molecular formula. The first part is the atomic symbol. The atomic symbol tells us which elements are present in the molecule. We simply need to read the atomic symbols and identify the element that is represented by each symbol. In our example here, we can see that we first have a carbon, or a C, which tells us that there is carbon present in this molecule. We next have an H that tells me there is some hydrogen in this molecule. Finally, we have a Cl, which tells me that there is chlorine present in this molecule. The next piece of information that we can get from a molecular formula is from the subscript. The subscript is that small number that comes after the element it is associated with. So remember, when you're looking at a subscript, the small number comes after the element that it is associated with. In our example, we can see that 3 comes after the hydrogen, so that 3 subscript is associated with the H. The subscript tells us how many atoms of that given element are present in the molecule. So in our case, that tells us that we would have 3 hydrogen atoms in our molecule. Another rule to keep in mind is 1 means none. If there is no subscript written, we use the 1 means none rule. None tells us that the subscript is actually 1. So for both carbon and chlorine in our example, we see that there is no subscript. None means 1. That tells me there's 1 carbon and 1 chlorine present. The last thing that we want to consider when reading a molecular formula is the coefficient. That is that large number that comes in front of the formula. In this case, it is 4. This tells us the number of molecules that are present. So in our case, we have 4 of this molecule. So let's take a look at what this chemical formula is telling us. So we know that we have 1 carbon, 1 chlorine, and 3 hydrogens based on our analysis of this formula. So let's go ahead and put our molecule together. We have 1 carbon attached to 3 hydrogens, and finally 1 chlorine. Now we take into consideration our coefficient, telling us that there are 4 molecules present. So what we actually have here is 4 of this molecule, CH3Cl. Now, in order to find the total number of atoms, we simply need to take the number of each atom present in one molecule and multiply it by the coefficient. For example, we know that we have 1 carbon in each molecule. We have 4 molecules present. Therefore, to find the total number of carbons, I will simply multiply 1 times 4 and get 4. I would do the same with hydrogen and chlorine. In the case of hydrogen, I know that in 1 molecule, I have 1, 2, 3 hydrogens. I would simply multiply that by 4 and find that there are 12 hydrogens present. So now let's look at some examples of using the chemical formula to determine the structure of a molecule, meaning the type and number of atoms that are present. So in our first example, we're looking at Na2CO3. So of course, my chemical formula is just that, Na2CO3. So our first step is to determine the type of elements that are present. So all we want to do is go through and look at the symbols that are present in the formula. In this case, we have first Na. If I look at my periodic table, I will see that Na represents sodium. The next symbol that we have is C. You may already know, but if not, you look at your table. C is carbon. Finally, we have O, which represents oxygen. Our next step is to determine the coefficient. Remember, the coefficient is that big number that comes in front of the molecule. In this case, we can see that we do not have a coefficient written. So we want to remember our rule, none means 1. So if there's no coefficient written, we assume that the coefficient is 1. We also know that the coefficient is related to the entire molecule, so the same coefficient must be true for all of the elements that are present. Now we simply need to determine the subscript for each of the elements that we have present. So first we want to look at sodium. We know that the subscript is the small number that comes after the symbol. For sodium, that number is 2. For carbon, we look for that small number after the symbol, and we can see that again, there is none. So we remember that rule that none means 1, so we know that our subscript for carbon is 1. Finally, we want to look at our oxygen. We can see that our subscript for oxygen is 3. And now we're ready to determine the number of atoms. So we know that the subscript for sodium being 2 tells us that in this molecule, we have 2 sodium atoms. We also know that the subscript for carbon being 1 tells us that we also have a single carbon atom. Finally, we see that the subscript for oxygen is 3, telling us that in this molecule there are 1, 2, 3 oxygen atoms present. We also know that our coefficient in this case is 1, so we only have 1 molecule. Therefore, the number of atoms present are simply equal to the number of atoms in 1 molecule. So we multiply that subscript by the coefficient of 1, our number of atoms will stay exactly the same. So in this molecule, we can see that we have 2 nitrogen atoms, 1 carbon atom, and 3 oxygen atoms. Looks something like this. So now we'll look at this second example, 2CaCl2. So our chemical formula is, of course, 2CaCl2. And I will put some brackets there to help us analyze. So first we'll identify our elements. First we see a Ca, looking at our periodic table, tells us that is calcium. And we see a Cl, which our periodic table will tell us represents chlorine. Now we'll look for our coefficient, that large number that comes in front of the molecule. We can see here that it is 2, telling us that whatever we have in here, there are 2 of this molecule. Now let's look for our subscripts. Looking at calcium, we see there's none written. We remember our rule that none means 1, so we know that the subscript for calcium is 1. We also know that that tells us that there is 1 calcium atom in this molecule. Now we look at chlorine and we see this 2, which tells us the subscript for chlorine is 2. That also tells us that in this molecule, there are 2 chlorine atoms. So now we can see that the structure of this molecule looks something like this. Now we have to take in consideration that coefficient. That coefficient is telling us that instead of having a single molecule of CaCl2, we have 2. We can now, by analyzing what we have, or by using our multiplication trick, we can see that we have, for calcium, 2 times 1 atoms, or 2. And for chlorine, we have 2 times 2, which gives us 4. And here we have the structure, the type, and the number of atoms present in 2CaCl2. Here we'll look at one more example that's just a little bit more complicated. So here we're looking at the formula 2Ba parentheses NO3 2 outside of the parentheses. We're going to go about this exactly the same way. We just need to think about some math rules as we're looking at this. So first, we'll do the same thing and identify our elements. We look at our periodic table for Ba, and we will see that that represents barium. Next, we will look at N, which we know stands for nitrogen, And finally, our O, which we know is oxygen. Next, we'll look for our coefficient. So I'll put my brackets here and I look for that big number outside of the molecule, which I can see is 2. Now we'll start identifying some subscripts. And here's where we just need to think a little bit harder for this example. So first we'll look at barium. We can see that barium is outside of this parentheses and it has no subscript. So we can use our rule, none means 1, and see that in this molecule there is 1 barium molecule. So we can say in our molecule we have 1 barium. Next, we need to look at our nitrogen. However, we see something different here where our NO3 is inside of our parentheses and we have a subscript outside of the parentheses. Just like the distributive property in math tells us that a number outside of the parentheses can be distributed into everything inside, it works the same way with the chemical formula. So this 2 outside of the parentheses needs to be distributed into any of the atoms inside of the parentheses. That means that the subscript for our nitrogen is actually 2 times 1, which is 2. We'll do the same thing for our oxygen, which we can see here is O3 with the 2 outside the parentheses. So we'll distribute that 2 in, which tells us to multiply 3 times 2 to get 6. This tells us that in this molecule, we have our 1 barium, we have 2 nitrogens, and to each one of those nitrogens, we have 3 oxygens bonded. So 6 oxygens altogether, looking something like this. Now to finish up, we need to take into consideration our coefficient. So our coefficient here is 2, telling us that of this entire molecule, we actually have 2 of them, which means that the numbers in the molecule need to be multiplied by 2. So altogether, in this case, we would have 2 barium atoms, 4 nitrogen atoms, and 12 oxygen atoms.